silicon carbide power devices have very stringent criterion for deficiencies. How to improve yields through test and inspection processes while transferring from 150mm wafers to 200mm wafers?
Two questions, really. One of them is, how's the migration from 150mm wafers to 200mm wafers is happening? And the second thing, of course, is what in particular do you need to pay attention to when you get to the 200mm wafer? So today, silicon carbide is manufactured exclusively on 150mm wafers. 200mm wafers have been basically demonstrated in 2015. So from the point of first demonstration to the actual wafers being commercially available in production, there's a 7 to 8 year gap. So somewhere in 2022, 2023, we're going to start seeing 200mm wafers in the marketplace. Now, two things need to happen or are desirable to get there. The first thing is that the number of defects per centimeter square on the 200mm wafer, they need to be comparable or lower to those of the 150mm wafers. So basically the quality of the material when you go from 150mm to 200mm needs to stay the same. And a lot of the work in releasing 200mm wafers is in making sure that the defect density, the quality of the material is similar to what you have at 150. And remember, when you go from 150 to 200, it is really the area in the periphery where you're increasing the radius that contains a lot of the defects. So a lot of the work is to clean up that area and make sure the yields are good and comparable to what you have at 150mm. The second thing, of course, that's very important is cost, right? Cost comes into everything. You want to make sure that the cost of the 200mm wafer per centimeter square is the same or less than the cost of the 150mm wafer per centimeter square. So that's highly desirable. Now, fabrication on 250mm wafers, the fabrication cost is more or less the same, whether it's a 150mm or a 200mm wafer. And that's because in fabs, the majority of the cost comes from the large overheads. So whether you're processing a 150mm or a 200mm wafer, the cost is approximately the same. And when you do process a 200mm wafer, you're going to get 45% more material. So that's going to bring the device cost down. However, you need to pay more for the wafer itself. So assuming you go to a 200mm wafer, you get 45% more material. And assuming that your cost for the 200mm wafer per centimeter square is the same as the 150mm wafer, depending on your specific numbers, it will bring you anywhere between 17 to 22% in cost reduction for the device. Given the high demand of silicon carbide, it's definitely the way to go. So what happens now with the test, the inspection, and the yields when you get to the 200mm wafers? A couple of things you need to be vigilant about is number one, what are your yields going to be towards the edges of the wafer? Because it's usually the edges of the wafer that contain defects when you increase the size of the wafer. And the second thing is the planarity of the wafer. Even for the 150mm wafer, the planarity is really bad, so to speak, relative to that of silicon. So when you go into a silicon foundry where people are trained to have very flat wafers and do the processing, if your wafer is not very flat, that is a problem. And then silicon carbide has some high temperature processes, particularly when you do the implantation anneal, which is typically done at 1600 to maybe 1800 degrees. And at that point, if you start with a wafer that's not very planar, and you go to those high temperatures, your wafer can actually really turn into a potato chip. I mean, it can warp pretty badly, and then it will no longer be able to go through your stepper. So when you get to the 200mm wafers, and that's part of what people are looking at, is make sure you have a structurally good wafer with good planarity. At this point, we'll control most of the defects. The really big catastrophic defect at this point is basal plane dislocations. Basal plane dislocations can basically kill the device, so to speak, but those can be detected at the test and inspection level. The one situation that is still kind of a reliability concern is the threshold voltage instability. The interface between the silicon carbide and the gate oxide is relatively poor. It's got a lot of interface traps. That is a processing issue. You want to make sure you have a very good silicon carbide and oxide interface. It will minimize or eliminate the threshold voltage instability, which is a reliability concern, number one. Number two, if you get a better interface, then your resistance will go down. You will have higher performance devices.